So now for part two, what we need to do is calculate the net flow rates and the root finding to constrain the net flow of the internal nodes to 0. That's because we want the flow that's going in to equal the flow that's going out. So what we're going to do is look at this drawing, and we have node 0, 1, 2 in the environment, which is going to act as node 3. And we're going to start by making an array of all of these lengths, k values, diameters, from including like what node is it starting at for the pipe to what node is the pipe ending at, in order to help us find the net flow rates. So now what we want to do is make an array for all of the pipe's information. So we're gonna make a comment here to tell us what each part of our array is going to be. So array of pipes, and the first thing is going to be the from node, which is where the water will be coming from, and then the next will be the to node. Next will be the length of the pipe, then our k value, and then we will do the diameter of the pipe. So we're going to go ahead and say pipes is equal to np dot array, and our first first pipe section is going to go from node 0 to node 1, and it has a length of 20, a k value of 1, and a diameter of 0.1. I forgot the comma there, and this does not need a comma at that point. All right, and then enter, and our next length of pipe is going to be from 0 to 2, and that has a length of 30, a k value of 1, and the diameter is 0.01. Our third section of pipe is going to be from node 1 to node 2, and that has a length of 5, a k value of 1, and its diameter is 0.01. And the fourth length of pipe is going to be from node 1 to node 3, which is the environment. I didn't put this in brackets. Same with this one. Okay, yeah, it should be fine. So from node 1 to node 3, which is our environment, it has a length of 0.1. The k value is 6, which is an approximate guess that was given to us in the problem statement. And then the diameter is 0.01. And our last section of pipe is from node 2 to node 3, which is the environment. Has a length of 0.1, a k value of 1, and a diameter of 0.01. And then I need to close that bracket. That closes this one. I'm missing a bracket here, I think. Yes, I am. So let's see if that works. All right, and it did. So now to make sure this works, we can call a row of our array. So we're going to go ahead and do that. And the language we're using indexes at 0. So when I put 0 in here, I should get the first row of our array. 0, 1, 21, and 0.1. And I did. So for now, we're going to go ahead and delete both of these and keep typing in this block of code. So now what we want to do is make an array for our heights, or our z values. So z is going to be equal to np.array, and our height at node 0 is 15, and the heights at all of our other nodes, including the environment, are equal to 0. So now we can do z 0, shift enter, and we should get 15, because that is calling for the first part of our array because the indexing starts at 0. Now we're going to go ahead and delete both of these and keep typing in this block of code. So what we want to do is index our external nodes. So the external pressure indices are going to be equal to 0 and 3, because those are our external nodes. 3 is the environment. And then next what we're going to do is put what the pressures are at those nodes. So external P is going to be equal to np.array. And the external, or the pressure at node 0 is 0, and it is also 0 at the environment, or node 3. So then shift enter. So we can go ahead and check that. So external P, 0, should give us 0. So up here, we made a note to ourselves what each part of our array was going to be. So the first column is the from node, and then the to node length k diameter. But we need to tell the actual code that. So we're going to start by deleting these. So the from node is going to be equal to pipes, and we're going to put a colon here, and that colon is going to tell us that we want every single row in the column, and it's going to be a 0 because that is where index is at. And we're going to go ahead and make this an integer, so we need as type np.int 32, and that changes that to be an integer. And so we're going to do that for all of these. So the to node is equal to pipes bracket. We can just go ahead and copy and paste this. And we need to change this to say 1 and include the parenthesis. Then length is going to be equal to this as well, where this is 2. And our k values are the third column, and then our diameters is equal to the fourth column, or the fourth index. So we can go ahead and double check some of these. So shift enter, and we're going to go ahead and do our from node. Let's do the second one, and what we should get is 1, and we did. So let's try the to node at 3. And we should get 3, and we did. Go ahead and delete these. Next, what we want to do is go ahead and put in the relative roughness of our pipes. Instead of making an array like this, since the relative roughness is all the same for all the pipes at 0.01, we're going to make an array that we will fill completely with just the 0.01 using a way to find the shape to figure out how many elements or how many pipe sections there are within this array. So what we're going to want to start with is finding the shape of that array, and to do that we are going to This is going to be number of pipes, so n pipes. Ooh, spelled that really wrong. Is equal to pipes, which is the name of our array, dot shape. And we're going to go ahead and put just the first, or I guess the 0 column, shift enter, and that should tell us that we have 5. If I go ahead and put pipes dot shape, and it's a 5 by 5. So if I do the first one, it should just give me 5. So from there, we're going to go ahead and just get rid of that part. We're going to do our pipe relative roughness is going to be pipe underscore ed is equal to np dot full, which is going to make an array completely full of the value that we say. Our first part is going to be the size of our array, so number of pipes, and then we're going to say comma 1 times e to the -3. So we can go ahead and double check that by typing in pipe underscore ed and shift enter, and that should give us an array that's 1, 2, 3, 4, 5. It has a size of 5, all with the relative roughness of 0.001. So go ahead and delete these now. So next what we want to do is write out how many nodes we're going to have. So number of nodes. We could just say it's equal to 1, 2, 3. We could just write 4, but there could be a time where we need to use this code again, so we should just go ahead and automate it. So the number of nodes is going to be equal to np.max pipes, which is our array, and it's going to go through our array and figure out how many nodes are going to be in there. So colon, because we're going to look through all the rows from 0 to 2. And we want to go ahead and have this as an integer, so as type np.int and then +1, because we want to add 1 for our external node. So let's go ahead and check that. Model numpy has no attribute in 31. Oh, this should be 32. So now if we shift enter, should be fine. So next what we need to do is figure out the internal indices and nodes. So internal indices is going to be equal to a list we're going to arrange the number of nodes. And we want this as an integer, so dot as type, and then np numpy integer 32. And we're going to subtract the external pressure indices from that. This will give us just the internal indices. So basically what this is doing is taking all of the indices, and now we're going to subtract the external ones in order to get just the internal indices. So we can shift enter. Oh, this should be a period and not a comma. I added an extra R. All right, so then internal indices should now just give us 1 and 2 because our external indices are 0 and 3. So this part gives us 0, 1, 2, and 3. This part then subtracts 0 and 3 to give us 1 and 2. So go ahead and delete these and we can move on to the next step. And so this gives us the internal indices, which are 1 and 2. Next, what we want to know is the number of internal indices, which we know is 2, and we could just say equals 2, but if we ever wanted to use this again, we're just going to go ahead and automate it. So length of parentheses, internal indices, shift enter, and then internal indices. When I shift enter that should give us 2. And it did. Go ahead and get rid of those. So next what we want to do is we're going to set our flows equal to an array. We want our flows from each pipe for right now to be equal to 0. We're going to fix this in later parts so that the flows aren't actually 0, but we're going to go ahead and make this array. We could use np dot full and then the size comma 0, but there's another way we can do that. We can just put np dot zeros and the size. So flows, there's going to be a flow in each pipe, so we want it to be number of pipes. And we're going to go ahead and do this with the net flow rate, which is going to also be np.zeros. Except this one, we want the flow rate at each node. So instead of using the number of pipes, what we're going to use is the number of nodes. And then we need the pressures at each node, and we're going to go ahead and say that's also equal to 0 to help simplify our equations, and we need it to be the size of the number of nodes. We're going to do this with the heads, and the head at each node, so np.zeros for the number of nodes. Shift enter. So then if I type in heads, that should give us zeros, an array that is size 4 because that's how many nodes there are of all zeros. And if we go ahead and do that with flows, that is going to give us an array of all zeros, but instead of there being 4 elements, there will be 5 because there are 5 pipes. Go ahead and delete these now. So next what we want to do is set the external indices pressures equal to the external pressures. So pressure at the external indices is going to be equal to the external P. And we can go ahead and shift enter that. So now what we need to do is find the internal pressures, or the pressures at the internal nodes. But in order to do that, we need to make a guess at what the internal heads are, because the internal pressures is going to be equal to the head at the internal nodes minus the heights of the internal nodes multiplied by the density and acceleration due to gravity. So in order to do that, we need to figure out a way to guess for what, we need an internal guess for the heads. A good guess would probably be using the external heads. So we have 2 external heads, so if we just take the average of that, we can use that to find a decent guess for our internal head guess. So that's going to be np.mean. We'll take the average. What we need is the external pressures, so external P, and that's going to be divided by rho, which is our density divided by acceleration due to gravity, plus the heights at the external pressure indices. And this should actually be brackets. So now if we want to make an internal guess for the heads, we can use this average external guess to help us. So we're going to make an array that is the size of our internal indices, or the number of internal indices. So that's going to be internal indices, and what we want it to be filled with is the average external head guess. So now if we want to go ahead and double check that this works, we can do the internal head guess, and that should give us an array with two elements that are the same, and that's what we get with the internal head guess being 7.5. So we can go ahead and delete those. And now that we have an internal head guess, we can find and guess for our internal pressures. So the internal pressure guess is going to be equal to the internal head guess minus the heights at the internal indices and that is going to be multiplied by the density of water and acceleration due to gravity. We can shift enter, and internal P guess is equal to an array with two elements because we have two internal nodes, and they should be the same at 73,575. We can go ahead and delete these now and go on to the next step. So now having done that, we can hit shift enter again and check to see what our pressures are going to be equal to. They should all be 0. So if we were to take the internal P guess and do the pressure at the internal indices, this should be lowercase. There we go. And then set that equal to internal P guess. We can shift enter, and what that will do is set the nodes that are 1 and 2, put those pressures that we guessed in for here. So we can go ahead and now shift enter that, and we get an array with 4 elements with the external nodes being 0 still, but then the values that we got previously for the internal nodes of 73,575 being inserted into our array. So now what we want to go ahead and do is make a function so that our net flows will go to 0 for the internal nodes. So we're going to use the internal, there we go, pressures. So we're going to use a thing called global, which will search through all of our blocks of code for the various variables that we put in. So we're going to put in heads, our net flow rates, our flows between the pipes, and our pressures at each node. And we're going to define heads is equal to the pressures at each node divided by the density of our fluid, which is water, divided by acceleration due to gravity, and that's going to be adding plus z, which is our heights at the nodes. So now what we're going to want to go ahead and do is calculate the change in heads and the flows for all of our pipe segments. So to do that, we're going to use a for loop, because that'll make the calculation more compressed and easier without having to write it out for every single pipe. So for I, which is our iterations in range, we're going to use the range of our number of pipes. So n pipes, and we need a colon after that. And so to calculate our delta head, that is going to be equal to the heads at the 2 node these should be brackets. So the head's at the 2 node, and we need to put our iteration in for I, minus the heads at the from node for iteration I. And we also need to do flows for I. And that is going to be equal to the flow of our delta head, our lengths, our K value, our pipe diameters, and then our relative roughness of our pipe. So we want to go ahead and double check these. So we're going to shift enter and use the function here. So Q to 0 for the internal P guess. And we will shift enter. Diameter is not defined. Because I called it diameters. So go ahead and change that. Shift enter and shift enter. D head takes 4 positional arguments, but 5 were given. Okay, so my power went out, so we're gonna redo all of these. That fixed my error. I don't know why. It said that it was here. I had too many arguments. Oh, probably from when I entered in K to make it more realistic, like for the Churchill equation or for the frictional factor part. I probably didn't restart this one or this one. That could be why. So now with this working, we can go ahead and shift enter and start to write a new line of code. And nothing popped up, but we should have our flows now because we have the net flows to 0 for the internal guesses, for the internal pressure guesses for the nodes. So now if I type flows, I should get the flows between each node. And I do. I get an array with 5 elements, which makes sense because there are 5 pipes. So if we go ahead and type in our 2 node, we'll see that we have a pipe going from to 1, 2 pipes going to 2, and 2 pipes going to 3, where 3 is the environment. So we have our flows for each pipe. What we need to do is add up the flows that go to the same node. So there are 2 that go to node 2. We need to add up both of those flows to get the flow at node 2 so that there is a net flow of 0 for the internal nodes. So in order to do that, we're going to use numpy add at, and that's going to help us add the flows that are at going to the similar nodes. So we need net Q, which is the array where the flows are going to be stored. We need the toNode, indicating the locations where the flows are so that those are what need to be added. And then finally we need flows for the actual flow rate that will be added. So I did forget something. So when we go through this iteration, our net Q the first time is 0, but then the next time we go through the iteration and all the following times after, net Q will no longer be 0. So what we need to do is after this, add, we need to fill the array with zeros. So that'll make sure that every time we go back through the iteration, our net Q is 0, where Q is our flow rate. So we've added the flows that are going to the node, but we need to subtract those flows from the from node. So what we're going to use is np.add again with net Q, but instead of the toNode, it'll be the from node. And we need to subtract the flows, so we're going to put a minus sign in order to subtract it. And we will return the net Q for the internal indices. Oh, it's outside the function. That's my bad. Let me just copy and paste this and put it back in the function. We're going to go ahead and delete these so they're out of the way. So these need to go here, yes. And now it should work. All right, there we go. So we're going to shift enter and that worked. So now we're going to go ahead and look at our net flows. And it gives us an array of 4 net flows, but we want these 2 internal net flows to be equal to 0. So in order to do that, we need to use the root function, so root. And what we need to put in that root is the function that we want to find the root of a vector of. So we want that to be q to 0, because this is going to return us the net Q values for the internal nodes. So when we put Q to 0, we want those 2 unknowns, those 2 net flows to be to 0, with the x naught being our initial guess. So that is going to be internal P guess. Oh, net Q is an array. So I think these should be brackets. Let's find out. Oh. There we go. All right. Oh, shoot. Net Q, an array, and there we go. So now we want to be able to print these, so we're going to use a for loop again to go through the iterations. So in range of our number of nodes, need a colon, and we're going to print f net q for I. All right, so net q, we need brackets for I, 5 F, and to close that, yes, 1, 2, 3, 4, P semicolon, or that's a colon, 0 F. All right, and now we have our net Qs and our pressures. And then we need to also print more. So now we are going to print for I in range of N pipes, print F from node with our index to node with our index flows and our index. So then colon 9.5 F meter cube per second. Shift enter. So looking at what we got, our net Q for our internal nodes have not been zeroed out, which are giving us the wrong pressures, which will then give us the wrong flow rates. So I'm going to go back through my code and figure out why that's happening. All right, so looking at what we get, I feel like there's an issue with my pressure where I never like redid the pressure, maybe, because I have getting it to 0. Oh, because I only have the internal nodes, internal pressures equal to the pressure guess. I never put back in this part. So I need to say that the internal indices, so the pressure at the internal indices is going to be equal to the internal P. So hopefully that fixes it. Go ahead and run all of these again. And we get the internal nodes flow rate being 0, which is good. We have the pressures here being 0 because they were supposed to be. So we have now solved for the missing pressures that we were needing to find for node 1 and node 2. We can look back and find what the flow rates were to the environment from node 1 to 3. And it was 5 times 10 to the negative 4th, which this is approximately equal to that, 5.4 times 10 to the negative 4th. But from node 2 to the environment, we have 4.7 times 10 to the negative 4th, when it should be 2.5 times 10 to the negative 4th. The reason for that is for 2 to 3, we had to use those initial guesses for Z and K, where at node 0, the Z value was 15 meters and that K value was 6. So if we were to alter the Z value, we could get the flow to decrease to where it needs to be at 2.5 times 10 to the negative 4th.